Obviously, I guess Jane followed me. I was a student. I was finishing when Jane started, and obviously I did not benefit from Jane's and Debbie's eyebrow theory. It might have been very useful. Certainly see a lot of faces in the audience who were there are contemporaries of mine. John and Charlie. And I guess we'll change. I guess we've changed gears, coming from way out, at the beginning of the universe, back into our neighborhood, or the solar system. And certainly, as with the interstellar media, atomic and molecular physics play an important part of that. And certainly, the role of Alex Dalgarno has certainly been very basic. Again, pioneer in that work for many years. So, what is the role of atomic and molecular physics? It's just almost impossible to enumerate. It's basically a whole field. It's whole decades worth of work, but basically, it controls basically the solar corona, for example, which then controls basically the aeronomy of basically all the planets. Atomic molecular processes control the ionization balance, controls the emission features of the solar corona, impact ionization, excitation, dielectric recombination. Once you have all these extreme ultraviolet and X-ray photons, they then encounter planetary atmospheres. They create ionospheres due to photoionization. You certainly have electron impact ionization and auroras and due to photoelectrons. Then you have the whole slew of ion neutral chemistry, and Alex has played a particularly important role in this regard. You have then dissociative and radiative recombination, and it goes on and on. Heating, air glow, superthermal processes. Relatively recently, atomic molecular processes have been playing a role in understanding how our solar wind interacts with the local interstellar medium. For example, carving out a cavity in the incoming atomic hydrogen. And in particular, one recent diagnosis of this is the X-ray emission that's associated with charge transfer of highly ionized ions with neutral targets. This happens with interstellar gas, it happens with cometary gas, happens at Jupiter, happens at Mars, happens at Earth, the geocoronal, and Alex has been a key part of that effort, along with Vasily Kharchenko. However interesting that topic is, I will not talk about it. Vasily Kharchenko will have a talk later in this meeting, and after brief consultation earlier this week, we agreed that he would cover that. But there are no shortage of topics that Alex has contributed to, or you pick any planet or satellite in the solar system is relevant. So if you look at some of these objects for which Alex has contributed, Sun, Jupiter, every planet and satellite, basically the upper atmosphere, the aeronomy, and Earth, I didn't put Earth there, is controlled by atomic and molecular processes. And certainly the work Alex did, starting back when he was in Belfast, in particular, a lot of the stuff on ion-neutral reactions was particularly critical in this development. And again, it's hard to really even find a few examples. So I picked a couple really old ones that I was familiar with, and I picked some more recent ones, and not much in between. Although there's easily a couple hundred papers overall. Going back a ways, certainly what the work he did with Jane on Venus and Mars. Heating efficiencies, ionization, airglow efficiencies for Venus and Mars. I put out a book off my shelf even in putting this talk together. At the end of my talk, if I have time, I'll say a little bit about Enceladus. And I found very useful, there's a book called Ion Molecule Reactions by McDaniel, Cermak, Dalgarno, Ferguson, Friedman. Had some experimental stuff, had some theoretical stuff. And obviously, I didn't know which of these authors wrote what, but reading the book, again, looking at it recently, I suspect some of the stuff of scattering by complex potentials is probably Alex's, and stuff on Langevin rates and how they apply. I might point out in a couple places later where some things in that book are still very useful to this day. Besides, I like the year 70. That's actually when I arrived to work at Harvard. Okay, but more recently, there is the paper by Dargarno on cometary X-rays. There's ones by Denner et al., which includes Alex as a co-author on X-rays from charge exchange reactions at Mars. On another sphere, Alex has done a lot of work with Karchenko and others on how superthermal atoms rattle around upper atmospheres. What is their distribution of superthermals? How do they heat? What do they do? Jane did not talk about it. It was in her abstract, and I guess in her poster. Dissociative recombination interactions in superthermal atoms supply the hot oxygen corona at Venus and Mars, and also supplies escaping O atoms at Mars. Okay. Obviously, to save energy, I got this thing timing out too soon. And then again, as you will hear from Vasily Karchenko's talk, the whole bunch of things on X-ray emission due to the charge transfer of highly excited ions. And I will leave that and again, a lot of recent work involving Alex. Now, besides the work that Alex himself is author or co-author on, his sphere of influence goes far beyond just those however many papers there are, and there are a lot. If you look at former students like myself and Jane, former postdocs and colleagues, his sphere of influence is incredibly broad. Certainly I consider myself honored to be part of that sphere of influence, and sort of ripples, if you wish, of what he put into place. I might also mention ITAMP. That is very useful and has made a major contribution. Just thinking of the whole X-ray business, X-rays from Jupiter, X-rays in general from this charge transfer, certainly in terms of my thinking, and I know others, like Vasily and Peter Beersdorfer and others, the ITAMP workshops, there were a couple really key ITAMP workshops on X-ray processes, including one last July, a year ago July, which was, again, very formative and helped keeping that field going. And that ultimately stems from Alex's efforts. So, having done that, I will, in discussing it, since I'm not going to talk about all of atomic and molecular processes in the solar system, I'll have to focus. And obviously I will focus on something I'm working on fairly recently. And I'll talk about, and I put ion-neutral collisions because it's sort of a sub-theme that I'll emphasize throughout this. Essentially, that is actually ion-neutral reactions was the topic of that McDaniels et al. Book. Certainly the formation of an ionosphere of Titan. Why? Because I happen to be working on Titan. But it is a typical, quote, aeronautical example where atomic and molecular processes play a critical role. What creates the ionosphere? Photoionization, basically, and impact ionization, both electrons and ions. I'll emphasize the ions here. Certainly, ion-neutral chemistry has been a key part. We've heard about that in interstellar medium, all the ion-neutral chemistry in the early universe, the stuff Phil was talking about, Phil Stansel, H-. Certainly, ion-neutral chemistry is critical in any planetary ionosphere. Certainly, it is true at Titan, as we'll see. And if there's time, and we'll see what happens, don't give me a dirty look, Jane. Well, I'll skip that if I have to. No, I'm already anticipating the time crunch. Enceladus, something I just started looking at only within the last couple months. There is some interesting ion-neutral chemistry going on in the plume of Enceladus, which involves, actually, if you do it right, I think it's going to involve quite a bit of a detailed knowledge of the collision processes. So let me start with Titan. Let's talk about the haze layers. Why are we interested in this ion-neutral chemistry? It's now thought that a lot of this ion-neutral chemistry is playing a key role, not the only role, key role in developing the haze layers. The tholins that Sagan studied by zapping gas and creating gunk, because you really can't see the surface of Titan due to these haze layers. Ion-neutral chemistry is playing a key role in that. Positive ions and negative ions, I certainly won't talk all about that, we'll see. So that involves a very detailed knowledge of ion-neutral chemistry. To talk a little bit about that,
Our knowledge of this has really skyrocketed since the arrival of the Cassini spacecraft. Cassini had a probe, an orbiter. It was launched in '97 from a Titan IV vehicle at the Cape. It was in cruise for about 7 years, and in July 2004, lit its main engine, approached, went through the ring plane, went into orbit around Saturn. In January, in October, it had its first encounter of 04 had its first encounter with Titan, and then it dumped the probe in January, and since then, about once every month, it goes through the upper atmosphere of Titan. It's very well instrumented. It has ultraviolet spectrometers, has Langmuir probes, magnetometer, and it has energetic particle spectrometer, and it has an ion and neutral mass spectrometer. Not because it's the most important, but because I'm associated with it, I will emphasize that data. And that data certainly has a lot to do with atomic and molecular processes. So what is the upper atmosphere of Titan? It's mainly molecular nitrogen. This is just showing the density distribution measured by the ion and neutral mass spectrometer from an altitude of about 1,000 kilometers upward. The pressure at the surface is about 1.5 bars, denser than Earth's, mainly N2. Haze layers are from a few hundred kilometers up to about 900, so this is above the haze layers. And the next most important species is methane. And that is what makes the ion neutral chemistry interesting, is that methane, because it's a hydrocarbon. Now, in addition to these, the neutral spectrometer also saw ethylene, acetylene, hydrogen cyanide, benzene, perhaps some propane, and there's a bunch of stuff that neutrals it did not see. Now, that's seen in the thermosphere. In the infrared spectrum, some of these species were seen lower down as well in the stratosphere. And these neutral species then get ionized and create the ionosphere, which is really what I'm going to emphasize, is that really not the neutral chemistry, although that's very interesting. So what creates the ionosphere? Well, you've got to ionize these neutrals. Certainly photoionizations, as in any planetary ionosphere, if the sun is shining, that's probably the most important source of an ionosphere. And that is true at Titan as well. It wasn't entirely obvious, but that is certainly the case. On the day side, photoionization dominates by the extreme ultraviolet and soft X-rays. So you have to know all the photoionization cross-sections, the branching ratios, all that other stuff in order to figure out what's going on. But on the night side, certainly electron impact ionization is important. Well, even on the day side, you've got secondary electrons or photoelectrons. You know, those do contribute to the ionization, particularly at lower altitudes in the bottom side ionosphere. But also, we now think that ion impact is contributing to the ionization, particularly in the night side and the day side. And since my theme is a little more ion neutral reactions, I'll emphasize that here. And also, since I have to choose something to emphasize. This is a cartoon or schematic of Titan as it exists in Saturn's outer magnetosphere. So there's the lower atmosphere, there is the thermosphere, and up here with the thermosphere is the ionosphere coexisting with the thermosphere. Now, this scale is not entirely exaggerated. It's a rather, quote, spherical object. The scale height is quite large because the gravitational acceleration is quite small. Again, it is not a slab-like atmosphere. Not quite cometary, but it's more cometary than the terrestrial atmosphere is. Very extended atmosphere. Certainly, sunlight coming in here will ionize. Electrons will ionize. Existing in the outer magnetosphere, you've got trapped particles, trapped energetic ions, trapped energetic electrons. So these KeV electrons come down the field lines and will contribute to ionization. Certainly in some passes going to the night side, that is dominant. And certainly there's been a lot of work done on that. But in addition to that, it was not appreciated a little while earlier, that energetic ions also could contribute because there are energetic ions in the magnetosphere. Now what they might do is actually go deeper into the atmosphere than the electrons and the photons, and indeed they do. And that has not fully been taken into account. Big difference between the energetic electrons and ions is that the electrons' precipitation is controlled very strongly by the magnetic field configuration. Saturn's magnetospheric plasma with its field is partially co-rotating, moving around with Saturn. That stuff gets whipped into Titan. Titan acts like an obstacle. The field lines sort of get draped around, and those field lines control due to the small gyrates, the electrons, where those electrons go. For the ions, on the other hand, you take a few keV ions. It's a fairly weak field. The gyre radius is of the order of the size of Titan. Therefore, the magnetic field is not really shielding Titan too well from those ions. So the ions sort of, well, they're not going straight in, but they are not terribly inhibited by that field. So about a year ago, a few of us did some calculations. We took the measured energetic ions in the outer magnetosphere. And I won't linger on this, but these are just particle fluxes versus energy. Both for, well, at this point, it's not 100% obvious how much is heavy ions, O+, and how much are protons. That is actually the two particle instruments, there are two particle instruments, one at low energies, one at high energies, MeMe, are now trying to figure that out. Some of them are O+, some of them are protons. So we made two assumptions. Either they're all protons or they're all O+, and see what they do. Again, the particle fluxes are variable. Sometimes you're in what's called the plasma sheet of the magnetosphere, and the particle fluxes are high. This is, quote, the T5 pass. And sometimes, more typically, you're out a little bit in the lobes of the magnetosphere, the fluxes are lower. But you see ion fluxes from a few tens of keV all the way up to several MeV. And those, when they come into the atmosphere, and why you get those is really not an atomic and molecular problem, it's a magnetospheric dynamic problem, but their interaction with Titan is very much an atomic and molecular problem. Because you get ionization, protons plus N2 will give N2 plus, protons from N2 will, O plus ions plus N2 will give N2 plus secondary electrons. By the way, these secondary electrons could also contribute to ionization if they exceed the ionization potential. So you have to worry about those processes. Certainly charge transfer is important. O plus N2 will give you O. Thank you very much. O plus N2 will give you, will charge transfer and produce N2 plus ions. So you got several ways to get N2 plus ions. And certainly once you have the O, you could lose an electron and go back to O plus. In fact, you will have, in general, a charge balance that Vasily and others will recognize as taking place at Jupiter as well, but for more energetic ions. So you need to worry about all these things to see what's happening in the atmosphere. And if you take just the oxygen, the protons are simple. It's either going to be H plus or H. Oxygen could be either O or O plus or O double plus or O triple plus. That beam is depends on the energy. Lower energies, it tends to be a neutral beam. Few keV, it'll be O, maybe a little bit of O minus. Higher energies, it'll be a mixture of O plus and O. Very high energies, it'll be more highly stripped. What Vasily and others have done for Jupiter are way up here at O7 plus, O8 plus. Certainly that's something that Phil Stansel and Dave Schultz are working on with Alex as well for Jupiter. But at least for Titan, we don't go that high in energies. So what do these things do? Well, they deposit their energy in the ionosphere. As we'll see later, this is just some simple range calculations for a pure O beam and a pure proton beam as a function of initial beam energy, using those at basically cross sections and stopping powers from the atomic molecular literature. The main ionosphere is up here, but the radio occultation experiment did detect some ionospheric layers very deep. The question then came about, what is causing them? Certainly not photons. They're not going to get that deep. I'll show that. And difficult to get electrons. But these ions, because we were getting up a few few MeV, could get right down to about 500 kilometers altitude, well under the main ionospheric layer. So in putting this all together, using the available cross-sections in the literature, you could calculate the N2 plus production rate, or the CH4 plus production rate. I just show one of them, as a function of altitude. If you look at solar radiation for comparison, here is at basically the terminator, that is dusk or dawn. Here is in the middle of the day. I chop it here so it doesn't get in these other curves. These photons produce ion production at higher altitudes. Typical ionospheric layers. In the Earth, they would be the E and F regions. The electrons, energetic electrons, if you consider them from about a few tens of eV up to about 5 kilovolts, 5 keV, produces this curve. These energetic ions, and I won't go into the details, produce ionization very deep in the atmosphere. And it's very variable. If you're inside the plasma sheet, probably this curve is more relevant. Outside the plasma sheet, this curve is more relevant, as these basically energetic radiation belt ions interact. Now, what does it do? Well, once you produce ions, you got to get rid of them. So you basically, what happens is you have a whole slew of ion neutral chemistry, and ultimately then the ions will have to recombine, mainly via dissociative recombination, which is another atomic process, certainly, that Alex has done a lot of work on. So again, electron density is a function of altitude, and this would be the solar produced peak. These lower layers are due to the ion precipitation, and quite variable depending what part of the magnetosphere you're in. Now, I'll be honest, I won't believe these too much. These are pretty well known because we understand things. Trouble with the stuff at deeper altitudes are, evidently there are negative ions have been observed as well as positive ions, and those are not understood, frankly, at all yet. At Earth, the negative ions associated with oxygen species, O2 minus, things like that. Titan has very little oxygen. There is a little oxygen, we think, but not a whole bunch. So it's not clear what's driving the ion chemistry, negative ion chemistry. And we don't understand what the effective recombination rate coefficient is. So very uncertain, but certainly these ion beams are doing something. Those ion neutral collisions are doing something. Now, let me talk about the ion chemistry in general at Titan. And I'll move back up to above 1,000, to the main ionospheric layer. Why? Because that's where our instrument is observing. The spacecraft has not gone below 960 kilometers for a very good reason. It goes below 960 kilometers, you're not going to have a spacecraft anymore, and you could kiss $2 billion goodbye. But above there, the ion and neutral mass spectrometer is doing in situ measurements of the ion composition, which is certainly outstripping a lot of the modeling and outstripping a lot of the understanding of the ion neutral chemistry. And this is the first ion composition measurements measured at Titan. Just a few of the species. These are the mass numbers: 17 Daltons, 28 Daltons, 29, 41, just a sample. The one marked electron density was measured by the Langmuir probe. The one marked total is the total ion density measured by the mass spectrometer. Two separate instruments doing two separate things. And they agree fairly well at lower altitudes. Why they don't agree at higher altitudes is a separate instrument. You want to believe the Langmuir probe. I'll just leave it at that, okay? Rather than the mass spectrometer. But what species do we see is a function of altitude. I should be careful, not just altitude. As the spacecraft goes through, it's traversed a couple thousand kilometers, which is almost a Titan radius. Horizontal variations are probably almost as important, or actually in the night side, just as important as the radial variations or vertical variations. So it's not simply an altitude problem, sort of a broad layer of ionospheric density, produced, we think, mainly by electron impact. You go deeper, and right here, maybe ion precipitation is contributing something. What is the ion composition? Protonated hydrogen cyanide, HCNH+, is a very important species. C2H5+, basically, if you wish, protonated ethylene. And it timed out again. Okay. Certainly you see things like CH5+. Mass 18. Before the spacecraft got there, we didn't really expect much there. That's where water is. We know there's not much water on Titan. But now it's thought to be ammonium ions, NH4+, associated with a reaction of ammonia. And as we'll see, there are a bunch of hydrocarbon ions. I'll show the next slide later, including protonated benzene, some nitro species, C3H5+. If you look overall at what you see, this is actually the previous was a night side data. This is a day side spectrum, and I'll just show this, but all the ionospheres have a similar type spectrum. This is a average ion density versus mass number from 0 up to 99 Daltons. And the Earth's ionosphere is pretty simple. N2 plus, not so much. NO plus, O plus, O2 plus. 5, 6, 7 species, if you stay out of the D region. D region's a mess. Here, we are seeing dozens of species. This is HCNH plus, mass 28. This is C2H5 plus. Mass 30 was not predicted prior to the, not predicted at any abundance prior to Cassini. This is a new species deduced by a neutral not expected there, CH2NH, which will then get protonated and produce CH2NH2 plus, deduced from this mission. But again, here's mass 18, which we didn't expect, NH4 plus. This is CH5 plus. So the question is, and you notice a pattern here. The spacing is, not surprisingly, 12. Okay, and this pattern actually continues at much lower resolution because we get delta M much less than 1. The energetic particle spectrometer in ramming mode, if it's a cold plasma, sees these families continue on up past 200 Daltons. Negative ions have been seen at lower abundances than that. At 100 up to a couple hundred, they don't get very good mass resolution at all. They see things up to thousands of Daltons or AMU, very heavy. They think they might be PAHs or PAH minus, which certainly is maybe this is looking almost interstellar. The fact that in some aspects it is looking a little interstellar, and hence the chemistry might have something in common. So going on, let me show a chemical diagram that was actually published prior to Cassini, which is partly correct. Now I don't have one which is, well, we don't know quite what the correct one is. We haven't even corrected it with what we know because no one's bothered to draw another one yet. But this shows some of the complexity. You start with N2 plus, CH4 plus as the main ions being produced. They undergo a rapid chain of reactions with methane, ethane, acetylene, ethylene, hydrogen cyanide, and produce heavier and heavier species, which keep on going and going and going to produce spectra sets you see. Unfortunately, these things are mainly on the odd ion masses. What we're missing were a lot of the even ion masses. We had a few, but not a lot. Certainly, Fox and Yell suggested a couple there that got rid of HCNH plus back in, 97. Certainly more recently, Vuitton et al. Have suggested a bunch of new these nitro species to fill in those gaps, including the one I mentioned. And this is just the positive ion chemistry. So where do we think this is going? This coupled with the heavy negative ion chemistry, and as an example, here's the protonated benzene. That recombines dissociative, you're producing benzene rings, which we think is a main component, of the tholins and the PAHs, ultimately leading to haze. Now the details of this are still being hammered out, and there's a lot of uncertainties. But there's a lot of, if you wish, ion chemistry that is not understood that is being worked on. So I think Titan is turning out to be a very interesting laboratory for ion neutral chemistry. And obviously these things have to recombine as well, dissociatively recombined. So again, I'll keep the conclusion simple. How much time do I have? 20 minutes, okay. And so I can say a little bit about Enceladus. Okay, just quickly. Yeah, okay, atomic and molecular processes, they're critical, basically, to controlling this thing. Both the production of the ionosphere, due to photon absorption, due to electron impacts, due to ion impacts, the chemistry is important. And certainly recombination process is important and still need to be understood. How do those recombinations depend on electron temperature? Fortunately, electron temperature is measured in the ionosphere as well. So if you could find out, in the case of many of these ion species, we do know how the recombination depends on electron temperature. Some of them we do not. Some of the more complex ions we do not understand the dissociative recombination. That's a whole other area of the atomic and molecular processes that more work needs to be done by someone who is good at that sort of thing. It's certainly not going to be me, but atomic and molecular types out there need to work on that. So there's plenty of things that need to be done. The second conclusion just focuses on that energetic ion precipitation, since the focus on that. And certainly the energetic ion precipitation is interesting because it goes deeper than the main ionosphere. It goes right down into the stratosphere and can maybe give rise right down into the haze layer. So any ions you produce there will very rapidly, via this chain of reactions, maybe lead to haze. Now, why do you need the ions and ionization? Why not just work with the sodium? Well, ionization is a very neat way to break that strong N2 bond. It's not so hard to dissociate the methane. And then the stratospheric people have had models for a long time. Photon plus methane will give you CH3 and H and, and those radicals and develop it. It's hard to get the nitrile type species, the nitrogen-bearing species, and those ionizing photons are very handy, particularly if you could get it done deep with like these energetic ions, to break those N2 bonds and help form some of that haze formation type processes. Okay, a little bit on the plume, and this is sort of not fully pulled together yet, but it's interesting, and does involve ion-neutral reactions, so I thought I'd go into it. This is an image from the Cassini Visible Imager of Enceladus. Enceladus, Titan is out at 20 Saturn radii. Enceladus is at 4 Saturn radii, somewhat outside the rings. It's in the midst of what's called the E ring, which is a ring, a very diffuse ring of very small icy particles and gas. The inner magnetosphere of Jupiter, of Saturn, is rather different than Earth. It actually contains some neutrals, some hundreds of 100 per cubic centimeter of water, some H2O plus, O plus, thought to be produced both by the water vapor produced by the ring ice and largely Enceladus. And Enceladus itself exists within this sort of gunk it itself produces. What might be produced in the gunk is thought to be due to these sort of ridges or geological features in the southern hemisphere of Enceladus. This is, again, a Cassini image, credit to Carolyn Porco. You could get a lot of these nice images right off the JPL website, I might add. And it's thought to be venting water, basically geysers or plumes, like Old Faithful. This is a sort of a composite. Again, this is from the imager of sort of false color enhanced, so they could really see where the stuff is going, of light reflected from little ice crystals. So it's a mixture of gas and little ice crystals, very small stuff, 1 micron, and where Cassini went and is going to go. It's done E2 and E3. We have not done E4 and E6 yet. E2, which I'll show some of it because it's really the only published stuff, just grazed the edge of the plume. This is the Enceladus. This is about 250 kilometers. It's a small satellite. By the way, ice-coated. It probably has a rocky core, definitely has a thick ice shelf like Antarctica, and perhaps not very deep down some liquid. They're not sure about that. And the most recent one, where I'll show some data, but not a lot, is E3, went right through a dense part of the plume. So let me say a little bit about that. And by the way, Enceladus also exists within Saturn's magnetosphere, this sort of relatively gassy magnetosphere with these heavy ions and stuff. And this heavy magnetospheric plasma is slamming into this, in this view, say from the left, including the magnetic field. It slams into this plume. And there's this, and this is not gravitationally bound. This is just sort of almost cometary-like pushing out there, and mainly water vapor. So the question is, how does this magnetospheric plasma interact with this? What happens? And what do you need to know to understand it? This from the E2, which is published, the first one is from the ion and neutral mass spectrometer again. This is the neutral spectrum now, not an ion spectrum. The one I showed from Titan was the ion spectrum, showing that it's mainly water vapor. The plume is mainly water vapor, but there's also some CO2, some CO, some methane. And I guess in this paper, our team called it a comet-like, but then we got hammered for that, saying, well, no, we don't think it's really sublimating ice. We think it's sort of, people think it might be sort of radiogenically heated ice turning into the water in the vents, or maybe even a tidal heating, which causes this water, and says that's not like a comet. Well, the composition is certainly comet-like, okay? The fact that it's not gravitationally bound is certainly comet-like. So I think this spectrum doesn't look totally dissimilar from a neutral spectrum of a comet, mainly water vapor at mass 18, and certainly the cracking pattern from that. Oh, and this is just a little picture of the instrument. The instrument has 2 main modes, a neutral mode and an ion mode. Okay, and this is just in that E2 thing, as a function of time, the fact that the water density builds as you get close to the plume and then decreases as you go away from the plume. The density here, probably somewhere between 10 to the 5th, 10 to the 6th per cubic centimeter. The most recent pass that got closer to the density is up to 10 to the 8th, or 2 orders of magnitude higher than that. And in this first pass, we did not measure ions. In the second pass, we did measure ions. And the instrument really wasn't designed to do that, but we did get something out of that, as I'll show. So what is the neutral environment? Well, it's mainly water, some CO2, CON2, the peak density about 10 to the 8th. If you look at the column density from that, it's about a few times 10 to the 15th. If you take a typical ion at a few eV, take a typical cross-section for ion-neutral interactions, say from the McDaniel's book, book, then you're going to get the fact that as the external plasma tries to sweep through there, there is a collisional depth, if you wish, of a few. I mean, it's certainly going to have several collisions before it gets out of there. I might add that the photoionization is probably not as important as the ions convected in. Okay, so the external plasma environment, well, this gets a little tricky to explain in a short, 10 minutes? Okay. In a short period of time. The external plasma, again, is protons, water, from previous exposure to Enceladus. And it tends to be relatively hot. It's co-rotating relative to Enceladus at about 26 kilometers per second. Hot because the ions are mainly gyrating. So they're gyrating with a gyration speed also of about 26 kilometers per second. If you look at the velocity space, they form a ring in velocity space. So that's the distribution that's interacting with the neutrals. Once it hits the plume, it's thought it probably slows down some. The field, the electron temperature is a few eV here. It might be doing a little bit of ionization, the tail of that, but not much. And again, the ion seen by the energetic particle spectrometer did appear to be a ring distribution which had slowed down slightly. I won't really talk about that, but it would be relevant to the quantitative analysis. So if we look at what the ion distribution function is, again, it should be located on a ring. Certainly outside Enceladus, it is on that ring. Basically, as the ions gyrate and move, in space they look like this. If you plot them a velocity space, they'll trace out a ring moving around. The spacecraft relative to Enceladus was down there in velocity space. Unfortunately, our instrument in its ion mode is designed to look at a very cold ions. It's designed for Titan, really, not for Enceladus. Cold ions right in the sweet spot of the instrument. And we get very high mass resolution when we do that. The energetic particle spectrometer sweeps through a lot of velocity space, but can't measure delta M over M is very poor. So it's designed to do different things. They indicated that it's probably a ring. We could only see that little piece of it, ions that are almost at rest in Enceladus frame. So when we see it, we're only seeing a teeny piece of it. But what we do see, we could get a mass spectrum out of it. Also tells us that if it's a very fat ring, we're not going to see much. If it's a very narrow ring, we'll see much more of it and get a good signal. If for some reason the whole thing gets slowed down and cooled and collapses into a very cold Maxwellian distribution, we should see a lot too, although that's probably not happening. So again, this is still pretty tentative. We really weren't designed to do this. But if we look at mass 19, and we're down to about a total of 100 counts, okay? This is closest approach. The plume was right here, as seen by the neutrals, that 10 to the 8th. Mass 19, not much. Probably real, but not much. That diffuse, very hot background, and bingo, we see a whole bunch of ions right at the plume at mass 19, which we're interpreting as H3O+. On the other hand, we are expecting to see a whole bunch of H2O+. It is the main ion most everywhere in the magnetosphere. Mass 18, this is a scale of 2. The other scale went up to 10. The mass 19 would be up here. Really, if anything, less in the plume. Not more, less in the plume. And we know there's H2O+ out there. We represent it as a spectrum. We see that strong mass 19 peak in the mass spectrum. This you've got to be careful. There's a whole bunch of counts in 134 milliseconds. might be an ice grain hitting. The neutral instrument also saw a few of these spikes we think are ice grains might be hitting the instrument or the spacecraft. But this is a strong mass 19 and nothing really at 18. Probably you don't want to really believe much below about 0.2 there. There's stuff out there, but the densities in where we could see it are so low that you can't really trust it. So the real question is, gosh, we see a lot of 19 and it's got to be cold or we wouldn't see it, but we don't see 18. So the question is, okay, why do we see 19? Even more interesting, why don't we see 18? And why is it so cold? Well, what happens when this thing slams in there? So here's a little cartoon. Enceladus, the Plume. Here's the magnetic field. This is the gyro orbit to give you a feeling for the gyro orbit. The stuff is going around and around and around and through it. Here's the spacecraft. By the time it gets to the spacecraft, it's gone through quite a bit of the Plume. So what happens to all that H2O plus or O plus or OH plus as it slams into the water? Well, we get ion-neutral collisions, okay? You could go look in your copy of McDaniels et al. What we're supposing happens is by the time it gets through this gauntlet, only the H3O plus left, and a lot of it is pretty cold too. So, but the details matter and are still actually being worked out. Certainly charge exchange is important for momentum transfer and for populating the cold ring. Okay? For example, a fast H2O plus swirling around there at 20, 30 kilometers per second, okay, which were ranging from 20 to a couple hundred electron volts, will mainly charge exchange. What that does is good. It takes that water and immediately gives the charge to a water at rest, and then the ion starts all over. It is cold right off the bat. It is, it's put at that rest frame where we could see it. But then it starts gyrating again. So, you got to do more than that. However, at lower energy, so the most probable thing, which I might not get to, if you look at the experimental data for this reaction, is that at high energies, beyond a few eV, it will charge exchange. However, the lower energies, it does your typical ionospheric thing. It undergoes a reaction, not quite Langevin rate because it's a dipole molecule, but roughly Langevin rate. And then it will produce this very well-known reaction, which is why, by the way, cometary ionospheres are mainly H3O plus. But the details matter in terms, and particularly in this case. So, by the way, what happened to all the other stuff? The O plus, the OH plus? Well, all that stuff will react with water. Well, we should get a little O2 plus, but the O plus, OH plus gives H2O plus. The H2O plus then goes to H3O plus. So even the O plus and the OH plus via wave station at H2O plus become H3O plus. So maybe it's not so surprising that by the time it gets through it all, we're practically just seeing H3O plus. Why is it cold? Because it's basically because of the reaction kinematic. Well, and I might say, where does the details matter? How does that reaction work? H2O plus H2O. Does the H2O plus grab a H atom, or does the H2O grab a proton? If the H2O plus grabs an H atom, then it's not going to be slow. It'll continue rapid. If it happens vice versa, it'll be cold. So in this case, it matters. What happens at different parts of the ring is different as well. So, so there are a bunch of details here. This is not just a cold stuff at 300 Kelvin. There's a wide variety. So in order to do this, and I'm going to skip through this, there is some interesting experimental paper, actually, on superthermal H2O plus interacting with H2O with some time of flight. And the answer is it really is the proton abstraction, which is good news. It leaves the H3O plus cold, which is what we wanted to hear. And again, I'll skip through the cross sections and go to the summary. Okay? What the cross sections indicate, high energies beyond a few eV, charge exchange channel. Lower energies is this proton abstraction or H3O plus channel. And I think it is consistent with the mass spectrometer data, although again, someone's actually got to do this more quantitative. Okay, to summarize, there is interesting atomic molecular physics going on in the plume of Enceladus due to the interaction of magnetospheric ions with the water vapor. Might say the details of that collisional process, the atomic molecular physics is very relevant to understanding this problem and understanding the data. And also for populating the whole inner magnetosphere, I might add, of Saturn with these ions and this population of H3O plus. And I'll leave it at that.
How do you distinguish the very interesting protonated hydrogen cyanide from molecular nitrogen?
Strictly on theoretical grounds, okay? In our instrument, there is no difference. It's mass 28, okay? Period. However, based on modeling, we know that N2 plus reacts with methane very rapidly. There's no way you could have more than a very teeny amount of N2 plus left. So the answer is, experimentally, we don't know. That's a modeling supposition that it's H and H plus.
I think actually the issue is the high ionization potential of N2 plus, or of N2.
Which is why it reacts so.
Yeah.
Yeah.
I mean, you go from species with high ionization
Yeah, H and H plus has a much.
low.
Yeah, it's down the chemical
So
food chain a lot. Yeah.
Yeah, it's at the top of the food chain, and then it transforms.
But our
With
instrument.
chemistry.
But our instrument can't tell you that. That's your atomic molecular
I'll tell
knowledge.
you that.
That's your atomic molecular knowledge. Yes.
No, it's logic.
It's logic. Okay.
I'm fairly ignorant in this area, but in the terrestrial mesosphere, where you have aerosols forming during precipitation, you can affect radar backscatter. I'm just wondering, do any of these observations of Titan, you were talking about haze formation, do any of the observations of Titan include radar measurements? And if so, do you see the effects of dust formation or aerosol
The haze
formation?
on Titan has really been observed with basically the visible spectrometer and the ultraviolet spectrometer. Occultations of the ultraviolet spectrometer, there is a radar on Cassini, but it has not made any measurements in the haze. I mean, it shoots right down to the surface. I mean, it does interesting stuff. It's actually shown that there are lakes made of liquid methane and ethane, the radar. But they're not getting any signal from the haze layers. But there is plenty of good data from the visible spectrometer and also from the, visible imager, and also from the stellar occultations from the ultraviolet spectrometer, showing these haze layers. And they're very small particles. They're well less than a micron size, the teeny little things. And offhand, I don't remember what the Earth's mesosphere size is.
They're a couple nanometers.
Well, then maybe it's not all that different, really, yeah? I mean...
We have time for one more question. Oh,
Thank you very much, Jane. Tom, I would like to ask about this consequence of such amount of water. Yeah, because you show that a huge number of density of water molecules.
In the plume?
Yeah. What about OH? Trace of some observation of spectra or anything about OH?
OH.
Yeah. Do you have some kind of information about it?
Okay. Well, certainly our instrument does not specifically see OH. There's a difficulty with that. When we measure our neutral spectrum, okay, what we're really measuring is, if you wish, the cracking pattern, is the products of the electron filament in our instrument ionizing the water. So E plus H2O will give an H2O plus signal, an OH plus signal, an O plus signal. All that appears in the cracking pattern. We would never see much OH in there unless there was a lot. On the other hand, this plume gas is moving pretty rapidly. If you ask what is the photodissociation time, I mean, there might be some OH, but there's probably not going to be a lot. Now, there is probably, if you look at the larger evolution of the whole E-ring, some gradual development, not right in the plume, but in the broader cloud where the water could reside longer, some photodissociation could be in OH, because OH is in the plume, not in the plume, in the whole inner magnetosphere. The Hubble Space Telescope saw that. There's a signal at OH.
Okay. I think we have to go on.